things. I mean, a lot of stuff that I was thinking, do these guys get sleep or what is it? Because, I mean, there are mistakes where you got the right formula, then you plug the wrong numbers in. And I'm like, how do you grade that? I don't know if they didn't know what they're doing, or, you know, I don't know how if they just made a silly mistake. Justin Winter, Jeremiah Woody, George, Keaton, Jacob, Garcia, James Penn, and Trent Bridges.
Yes, sir.
Jack Ethan Mitchell, Ethan Mitchell, and Chase Cole. All right, I'm going to go over this thing. I ripped a lot of these from homework, and the way what happened? I've got the solutions, I'll post them for you so you can look yourself. I worked them out at MathCAD, and I've got the raw stuff written here too, but let me go through. Look, here's how it works with this one. First thing you have to recognize, if you follow me on this is omega, right there. If you follow me, guys, you can look through it. Do y'all follow me on that? That's omega.
Yeah.
So, and it's also, the next thing you have to see, it is in air. That's like free space. That means omega over beta is the velocity, or omega, really you could do it this way. You could say if you wanted beta, it's omega times square root of mu epsilon. I've got the solutions here, I'm just showing. This would be beta 1. Well, this is really omega over c, isn't it, class? So, there's beta 1, it's 0.105. Straightforward calculation, nothing. Matter of fact, if you did that homework that I gave you, you got this, actually, this very problem. I don't even think I modified the frequency. I'm not certain of that, but now the next thing they ask for is beta 2. Well, beta 2 you have to do this for. You got to get gamma 2, and that's really right here. What this is gamma is equal to square root of j omega mu times sigma plus j omega epsilon. Y'all remember this right here? And that's equal to alpha plus j beta. This would be 2, that's 2, that's 2. And that's what I get here. I call it gamma 2, so I get this. Does everybody see that, class? So it's just j omega times mu 0, it was not magnetic, times mu relative, which is 1, times the quantity sigma plus j omega epsilon. And this is not, it's not a good conductor. It's not a perfect insulator. It's in between. You have to do all the calculations on this. So this is beta 2 right here. It's beta 1 was 0.105, and beta 2 is 1.019. Now you may have, because of round off error, it might be a little different. Now I wanted the phasor form of E relative, right? All right. So first, to get E reflected. To get the E reflected, you have to get the reflection coefficient. And the reflection coefficient requires you to get eta 2. So to get eta 2, I take eta 2 is equal to the square root of j omega mu over sigma plus j omega epsilon. I think we all know that, right? So this is it right here, eta 2. And it comes out to that, or it's this at an angle, and I don't know if I put the angle here, but there's an angle. Where is that angle?
43.5.
Yeah, that's right. 5, 6, and that becomes very important. Now, to get the reflection coefficient, and I think I called it ref, yeah I did. It's eta 2 minus eta 1, that's here. This is really gamma. Eta 2 minus eta 1 over eta 2 plus eta 1, and it comes down to this, right? Or it has a magnitude, I think I've got it here. Oh, maybe I don't. But this will come down to a magnitude at an angle, and the angle is 174 degrees. And the magnitude, where is that?
Should be point.
89. Oh, this is the whole magnitude for E reflected is that. Now, I asked for the phasor form. No, people gave me the time domain form. Some people gave me the phasor form. For the reflected wave, the phasor form would be magnitude of gamma reflected, the reflection coefficient right there. Then it's going to be times the magnitude of E incident. Then it's going to be E to the plus J beta Z. The reason it's plus is it's going in the reverse direction. It would be beta 1. Does everybody follow me on that? If it was going in the positive Z direction, it would be minus J beta 1Z. This is the reflected wave. Then you would have to have the phase angle here, which is E to the J 174 degrees, or what is that in radians? Some people, it was 3 points something 02 radians. I forgot if that's exactly. Somebody left it in radians. You left it in radians, didn't you? But it's going to be a plus J there. Are you with me with that?
Do you not want it in radians?
I didn't care if it was radians or degrees. I wish you would indicate radians or degrees, because when I just see a number there, and I'm bad at that. If I see it's the right value in radians, I know. If it's the right value in degrees, I know too. All right, class? Now, the next one is E transmitted. For E transmitted, remember there's an alpha, right? Remember that this beta 2, that gap, this propagation constant 2, this has an alpha and a J beta. Well, the alpha of that, where is that? The alpha is that, isn't it, class? That's an attenuation. That gets in there. So that means for this one here, now you're going to, well, let me get the transmission coefficient is right here. It's 2 times A to 2 over A to 1 plus A to 2, or just 1 plus reflection coefficient. Either one is fair. But remember, that's a magnitude and an angle. It's not just the number. And a lot of people ignore the imaginary part, and they paid for it because they lost points. So don't do that anymore. Now for this one, if you follow me on this, please do. This one, I wanted to write this. I didn't want to just type it in there and have you looking. This is going to be magnitude of the transmission coefficient times magnitude of E naught incident. Then it's going to be E to the minus J beta 2 Z. That's this beta 2. Then it's going to be E to the J, and that's now you got to get the angle of this transmission coefficient, and that's 40.689 degrees, I believe. And it's plus J 40.689 degrees. Are you with me? Now, after that, I gave everybody full credit on the VisWork because everybody put the right equation down. You had the wrong values for the reflection coefficient, but the right equation. I'm not going to punish you twice for the same mistake, kind of deal. I was just let everybody have that one as a freebie. So the reflection of this VisWork is going to be 1 plus the magnitude of gamma L. I mean, if it was right, if you had that over 1 minus the magnitude of gamma L. That's a reflection coefficient. I put an L there. You didn't have to. I could put gamma just by itself. And that value should be, this value, I didn't give you this value. This value should be, I believe, 89, where is it, 89.784. Sorry, wrong one. This is 89.784, and this value has a magnitude of, where is that? Where is 14, I think. Do I have it here? It's 14.1. 14.1 is the reflection coefficient magnitude times the incident field. Follow me, class? Now, I didn't think that was hard. Do you remember this for homework? You did this problem? I really thought it was a gift, but I found out there are a lot of people, this is my guess, either you're very tired that time or you've been skirting a lot of this and trying to cram it. I'll warn you about cramming. The next day, if you cram a cajillion things at night before, you're going to get so confused when you try to re-spurt some of this stuff out. And it happens all the time in my classes. And I'm being honest with you. I think that there's a lot of bright kids here. I think a lot of those mistakes were unnecessary. You just were doing some foolish stuff. So I didn't try to make that hard, all right? Now the next problem, I have this, but I'll tell you how the next problem, how I do it. I've got this as the general solution for you, but let me just tell you, I'll show you this in a second. Here's how I would do it. First, they give you an E field, right? And I'm just going to put down the E field. I don't care what these constants are. It's A to naught in this case. A to naught I naught, and it's over pi r, right? And then it's times sine of, times e to the minus j beta r times the sine of theta. And it's in the a theta direction. And they want to know directivity and radiation resistance. So by looking at that, you don't know what kind of antenna. You don't know if it's a loop antenna, you don't know if it's a short wire, you don't know. But it sure looks like at least it's a dipole by the sine, or it's a small antenna because of the sine theta. And some of you just guessed it's got to be 1.5, and you got some credit for that. Just a lucky guess. There was no evidence from any of your work. But here's what happens with this one. You take this from E field, then you get average power density, which some of you did right. 1/2 times magnitude of the E field, right? Squared over eta naught in the AR direction. That's average power density, correct? I'm just telling you, that's what it is. So what would it be? It would be 1/2 magnitude of the E field, and I'm going to square all this junk. It would be eta naught I naught over pi, right? You drop the e to the minus j beta r, take that thing squared, 1 over r squared, then sine squared theta in the AR direction. Do you all agree with that? That's P ab. Now, if I want directivity, the way I showed you to do this, I'm going to take P ab and I'm going to normalize it to get P normalized. And this is only going to be a theta. And when you do that, you'll notice all these constants go away, and you simply get sine squared of theta. You with me with that? Are you, what is, when I say the normalized power, it means you find where the maximum power is. Maximum power would occur when theta is 90 degrees, isn't it? Sine would be 1. So that's the maximum. You divide the maximum power into the average power, so it gets rid of all the crap in front of it, and you have just sine squared of theta. Does everybody agree with me? By the way, does anybody remember this problem? We did this. Do you remember the yeah?
I remember doing it, but I actually solved the omega p, the angle, in MATLAB. So I never.
Well, I did this whole thing. It's you're going to see this. That's the normalized power density. Now I know directivity is really 4 pi over what's called the solid angle, right? And that solid angle is equal to the integral, double integral, of the average power density, sine squared, or normalized power density, sine squared of theta times sine of theta d theta d phi. Theta goes from 0 to pi, and phi goes from 0 to 2 pi. You all remember that? Now that requires that either you got a symbolic, I mean, you use your calculator to do the integration, and some did, I'm certain, because the way it came out, it wasn't 8 pi over 3, it was whatever that number comes out to be. But this integral comes out to 8 pi over 3. And you all remember doing this integration class? Do you? I mean, it wasn't meant to be, it was I gave this to you because you did it. All right, everybody did, and you got a homework problem, 2 homework problems, I believe, with this. I might be wrong on the 2, but you got at least 1 with this very integration required. I think it's 2 actually. And there's, when you do this, what do you end up with? You get omega p is 8 pi over 3, right? Isn't that right? And then what's the directivity? 4 pi over 8 pi times 3, or 3 halves. So that's the directivity, and that's a quick way to get it. Now the radiation resistance is, you can do it a couple different ways, but since you have the power density here, I mean, this is the brute force way. This is the power density, isn't it? Average power density, right? So if we multiply that by a differential surface volume and just integrate over a surface of a sphere of any distance r, we would get the total power being radiated, wouldn't we, class? You remember doing this? Sure. So if I take this right here, and I'm going to say this is what I'm getting, P rad is equal to the integral, double integral of this, P ab, which is, I'm going to try to write it down. I do not like using this because I'm bending my neck and it hurts. Over 1 over r squared, sine squared theta. Now notice the integration. Now the differential surface is going to be r squared sine theta d phi. Do y'all remember that for the differential surface on a sphere? It's r squared sine theta d phi. Do you remember doing this, guys? I'm doing it this way, there's other ways to do it, this is the easiest in my opinion, but you can do it. I know there's little gimmicks. Now, the real point I'm making before, the bounds of this, the bounds go from where to where in terms of theta? From 0 to, and phi goes from?
0 to 2 pi.
All right, now, looky here. You'll notice the r squared here cancels the r squared here, correct, class? You know you're gonna get rid of that sucker. This is a constant, isn't it? That can come out in front, and what am I left with? 1/2 eta naught I over pi squared, and then I got that sine cubed integral, d theta d phi again, correct? And I know what the answer to that is. It's 8 pi over 3. I can do it, but I don't need to. I've just done it above if I've done my work. I mean, if you want me to do this integral, the sine cubed, you break sine squared to 1 minus cosine squared times sine theta, and just let u be equal to cosine theta, then du is minus sine theta, and it's an integration substitution. But this is what P rad is. But what is really P rad? Well, it's 1/2 times the radiation resistance, right? Times I squared, isn't it, class? I'm trying to be clear about this because a lot of people didn't even fashion the integral. They had P average right, but they didn't integrate it over a surface. And I didn't know if you didn't know the differential on a surface. I mean, the differential surface, that's just, do we all know r squared sine theta d phi is a differential? So you gotta know this in this class. You Teddy Mag 1, you use that all the time. All right, now, what are you noticing here? You see how the I squareds cancel? Make sure you see this, guys. And the next thing you notice is the 1/2s cancel, don't they? Can you see it?
Yes, sir.
Y'all see this here?
Is
The
that-
I squared's gotta cancel. If you get a radiation resistance that's dependent on I, that's a nonlinear problem.
Is that R rad? Is that what it's?
Yeah,
stands
that's
for,
right.
rad?
You're not gonna believe this, but I used to have good penmanship. Have you ever gone to a doctor's office and looked at a script? You know, doctors, if you look at what their writing's like before they start med school to after med school, it goes from legible to yucky to borderline non-intelligible to completely non-intelligible. And only the pharmacist knows because they call him. What does he mean? Because most of the scripts I see, I don't know what they're talking about. So I think they're writing the line, but they're not. You all see what I've done here? All right, now, next, you just plug in the numbers. So I've got eta naught, and that's 120 pi over pi times, and it's squared, times 8 pi over 3. And that pi cancels, so I have 100. Did I forget something? That doesn't look right.
Back in the P-Av equation, wasn't one of the eta naught supposed to cancel?
Yeah, that's true.
Wait a second.
Because
I'm sorry. I had an eta naught down here, my bad. You're absolutely right, I forgot the 1 over eta naught here. My bad. You're absolutely right, because that's 1/2 e squared over eta naught, and I didn't add the eta naught down here. There should be a 1 over eta naught out here. So that means one of those goes, let me put it down, it's 120 pi over pi squared times 8 pi over 3. And that means the pi's go, and I got 8 times 120 divided by 3, and I believe that's 320. You can check me on that.
yes,
Is that right?
yeah, because it's just 8 times 4, and then add 0.
Yeah, and that's 320 ohms, and that should be the right answer. Whitworth calculates the H field, then he does E cross H conjugate, and takes the real part of it times a half. Now this is the way I do it. I like my way better. It's less intermittent steps. But you got that problem for homework, I believe. Do y'all remember that or not? Anybody remember? No?
I don't remember a lot.
Well, at least you're honest.
Apparently.
No, I promise you, I'm not trying to put one on you. Do you all remember that sine squared, sine cube?
Yeah, I remember the
I
difference.
remember a problem with it, like I said, the book uses MATLAB to solve that integral.
Not
So
this one.
The homework I did.
No, MATLAB used the book used MATLAB to solve the integration for an arbitrarily long dipole, not this one. This ain't no dipole. This
Yeah.
was just a sine cubed integration.
Yeah, we did that integration a couple times, I remember that.
And it wasn't meant
I
to
didn't
hurt.
remember on Friday.
What?
Said
Yeah, I just didn't remember when it-
Fridays are the worst possible day for tests. I guarantee you, if I would have gave the same test to you on Monday, you would have scored, on average, at least 10 points higher. And I promise you, I'm not lying to you, I'm telling you the truth. It's something about, at the end of the week, exhaustion, fatigue. Monday is fresh usually, you're not, and you can usually do very well. I mean, most students do well, and I've been teaching for a long time, and I have watched Monday tests, they surprise me how well they do. Friday tests, are they that bad? Because some of the stuff that they do is just amazingly bad. And I think a lot of you, if you look at your work, you're gonna see that you knew this, you just somehow screwed it up in ways that I can't really explain. Now this is the next problem, and this is like, I didn't change anything here but the angle. I changed the distance r, I changed the actual power being radiated, but it was really a template problem. I just want to make sure you guys know how to do this. And most of you,
Said I like this one.
a lot of people got it right, but a lot of people still had problems, and I saw a lot of, they were uncertain about certain things, and I gave you the directivity for the 1/2, I mean, the only thing you had to do is the directivity for the short dipole, and I think I was pretty clear about it. When you're all is said and done and you turn the crank, you get this value right here. You all see it, class? Because it's just the straight equation, it's the Friese transmission equation. It's gonna be lambda over 4 pi r squared, right? Times the transmitted power, times the gain of the transmitter, which means you have to take into account the actual, it's a half-wave dipole, and it's actually bent, right? It's not directly in the bore side at 90 degrees, it's at, in this case, 60 degrees, right? Or 120, either one to get you there. And then you have to multiply it by the gain of the receiving antenna, which is going to be simply 1.5 times the sine squared of that angle to the normal, which is 80. That's it. Are you, I mean, that was fair. Come on, guys.
Yeah, I forgot part of the formula.
If you work these problems frequently, I mean, if you do them several times, and then when you review, you just do them one more time, it usually sticks with you. And the way I always get this, if you forget, always go back to the basics. Transmitted power over 4 pi r squared is isotropic power density, right? You multiply it by the gain, it sharpens it, right? Right? Now you have the average power density flowing. Now you just gotta catch it with the second antenna. How much do you catch? It's always lambda squared over 4 pi times the gain there. So that's how I do these problems in my head.
Wait, is this formula that I wrote down, is that part right?
Can you catch me after class?
Okay.
Let me get through the test, and then I'll answer any specific questions. All right, that's 3. 4. 4 is another one that I think this is the one I gave you for homework too.
We did this one in class too.
We did this, yeah, we did it in class. I gave it for homework, so I figure. So all right, a lot of people did get it completely right, but there were a lot of mistakes that they were saying, well, the 1/0 mode doesn't propagate, but the 2/0 does, or something like the 1/0 doesn't propagate, the 0/1 does. Regardless, there was a lot of stuff that there was uncertainty about things. You always take the long dimension as the A coordinate, and that's 8.636 times 10 to the minus 2. And there's B, so this is it. The cutoff frequency for the 1/0 mode is 1.737 gigahertz. The value of K based on that, because we're operating at 4 gigahertz, is going to be 0.9. Therefore, beta unguided is 83.776. Beta guided, of course, is beta unguided times K. And then the velocity, the phase velocity is omega over beta guided, or just however you want to do this, you could do it with K, is 3.3 times 10 to the 8th. the velocity of energy is just c squared over the phase velocity. And there are several other ways to do this. I'm just showing you the solution literally out of his book. It's a TE mode, so it's going to be the intrinsic impedance, or 120 pi divided by K, right? And after that, lambda in the guide is just lambda naught over K, and you get 0.083. You could have got that from beta in the guide too. Many, many ways to get these. It all comes down to one thing, just being familiar with the problem with waveguides.
So is phase velocity not equal to the speed of light in free space?
Yeah, in free space it is, but this ain't free space, it's a waveguide.
Oh, I saw the air field was through one.
If it's a waveguide, things are bouncing back and forth, and
Right.
you're never gonna have, unless it's extremely high frequency driving that thing, you're never gonna have that. Okay? Finally, and I thought that was fair. If you look through the homework, you can see where I picked these from. I mean, if you can't see where I picked that antenna problem from, or the Friis transmission equation, you really haven't been doing anything, because that was a given. Final one is 5. Consider a lossless half-wave dipole if the antenna delivering. This is the one we did in class, and I messed up. Remember this one? All right. It's delivering to the antenna. The antenna is delivering 1 milliwatt to a matched load. So the load has the 1 milliwatt, which means the total received power would be 2 milliwatts. Remember that, right? Remember this in class? All right, because I didn't listen carefully. It was the load that received 1 milliwatt. So 2 milliwatts are therefore received by the antenna, because half of it's dissipated in the radiation resistance, right? So then I have to calculate the open circuit voltage. I think you're the one that called me on it. No, you called me on it. Was it you?
Sorry, I was just looking, I added a pi for some reason.
I don't know where that pi came from. 2 people added pies and everything. How? They got honestly, they got for V open circuit, they had square root of 4 pi times R rad times P received. And I thought, okay, go ahead, explain this much.
I can't.
You just made a mistake, and that's a Friday test. You will come to understand, I'm telling you the absolute truth about Friday tests. In your lifetime, if you ever have a chance to do something big in front of crowds, don't do it on Friday unless you have to. Do it on a Monday, if you get to pick, or sooner. like on a Sunday or Saturday. Sometime when you aren't burnt out. Now for this one, it's straightforward. You got 1 milliwatt on the load, you multiply by 2, that's the power received. You want the open circuit voltage, so it's 4. 4 because you have 2 radiation resistances, right? It's going to be 4 times P received by the antenna times R rad of the antenna. That's the open circuit voltage. Then you simply build a circuit, and if you want me to, I'll build it for you. But it looks just like this. Then you put once you have V open circuit, it's a circuits problem. V open circuit, then you have 73.2, and you have J 42.5, and you have your load there, and that's 10 plus J10, and now you need I, and I is simply equal to VOC divided by, and that's going to be 83.2 plus J 52.5. And then to get the P received by the load, P load, that's simply going to be 1/2 magnitude of that value by magnitude, you don't put a J in there, divided by 10, because the only thing that burns real power is that 10 ohms. The J10 does nothing, that's reactive power. So you just divide it by 10. Correct, class? Remember that. You'll see this again. Now look, if you messed up, and I mean everybody I think could score better than they did, and I attribute it to a lot of things, but I'm going to tell you this much. The next test and the final exam, do yourself a favor. Think about, for the next test, the date you want it. Get your sleep and try to keep up with this a little more. I know a lot of people got stuff to do, but try to keep up with it daily. And I'm going to try to give you more challenging homework if I can. But I thought that was a very fair test, and I just thought that a lot of people were brain dead for some reason.
Yeah, I mean, I think it was fair. I think just the Friday test probably had most to do with it.
Yeah. Yeah, I thought that was.
There is nothing I can do to encourage people to not do a Friday test that I haven't done, but they still do a Friday test, no matter what I do.
We probably would have done an earlier one if we hadn't had all that
We had a lot of
other
stuff, we had communication stuff.
You can do it the next week.
Yeah, but then they would bring material to the test.
Yeah, then there was
You're
chapter
the guy
9
that
stuff.
wins the
on
lottery and complains about paying taxes. It really will help you if you don't take Friday tests, if you have the option not to. I don't know how Gross and other people do it. And I'll tell you what, really, if I can, I'll cancel Friday class, but I'm just level with you. I gotta be real careful. I got reporters calling me about why Dr. Leith left. I mean, I just got a lot of eyes on me right now. I get paranoid walking around campus. Anybody comes up to me and asks why, it's like, who are you? Why do you want to know? All right. I wasn't going to cover anything more today. I can if you'd like. But what I plan on doing on Wednesday, I'm going to give you a reading assignment, all right? And I'm going to ask you to take a look at some things. I'll give you maybe some problems. But we're going to be in the chapter on EMC. Now, this is an area I teach, and I do work in if I can. It's electromagnetic compatibility and interaction. The first things we do is we find out what things look like, resistors, inductors, and capacitors at high frequency. How all of a sudden an inductor has a capacitance associated with and resistance. How a resistor has a capacitance and an inductance, and how a capacitor has an inductance and a resistance. And none of these elements at high frequency look like what they're supposed to. They look much different, and that's the problem with when you do high frequency engineering. You have to know, even though you might say like 20 picofarads, that lead length might dominate the impedance of the frequency you're using. So you have to make adjustments. You have to do all sorts of things. Then we'll look at, here's a scoop before I let you out here. Then what we're going to do is look at actually how electromagnetic compatibility and interference is calculated. I'm going to go beyond what we're spoke, and we'll do some FCC stuff. We actually take a look at how signal is coupled from, say, my laptop into that phone. Is that a phone right there?
Yes, sir.
Right, into that phone. And I'll try to take you a little beyond what the text says and show you some tricks. And also, conducted emissions, this is another thing. If you've got something like a hair dryer, you plug it in the wall and you start drying hair, well, there's an electric motor in there, all right? That motor has sparking. The sparking and things like that literally cause a high frequency current interruption that gets propagated into that thing, into the wall, at 100 kilohertz or so, maybe even higher than that, and it propagates down there. If you plug in your TV, if you've ever seen this, you know what I mean, and all of a sudden you turn the hairdryer on and you see the TV get jittery. Or you can hear it sometimes if the equipment doesn't have good filtering. You can hear it in literally the audio feed too. Now, I'll cover some of those things. If you're an electrical engineer and you get a handle on this stuff, if you go out for a job, if you're at the front end of compliance engineering, it's after the design is done, they're trying to get it out the door, and now they go through the FCC tests, and the tests reveal they don't pass the test, but they can't redesign everything. They spent a fortune, getting the final device to this point. So what they go do is they go to the compliance engineers and they say, how do we fix this relatively inexpensively to get it out the door that'll pass the FCC test, or it'll be lightning hardened, lightning won't affect it, whatever it is. And we'll try to go through some things with lightning too. So they go through this rigmarole. Now those guys are super high paid. If the average engineering salary is $80,000, they're probably double that. And the reason, now not everybody can be a compliance engineer, but if you're a good compliance engineer, you're worth the weight in gold. It's very hard to tell you what you all need to know, but you need to know almost everything, because compliance engineering includes understanding all sorts of things like CRC error rates, and it includes things like understanding Freeze transmission equation, everything that you get from that you're learning in your undergraduate career, because there's no simple fix, is what I'm trying to tell you, or else they wouldn't pay you that much. The guys that I know are in compliance engineering, at least one, I believe, I might be wrong about this, I think he makes $500,000 a year, and that was 7 or 8 years ago. That's the kind of salaries these guys get. They're the big shots on the planet, because they can get product out the door. Now, that's not to say you don't need sales and you don't need designers and all that other stuff, but I'm gonna tell you, if it can't pass a test for the FCC, it can't be marketed legally, and that's a huge, huge setback. All right, guys. You got questions? Something you had a question? You had a question?
Yeah.
Okay, show me your question.
Can you go back to number 3, like what the answer
So,
was?
come over here. Almost right up here.
I made what you call a bullhead mistake.
And I'll put this up on, I'll put this, well, here it is. That's 3, right?
Yeah. What was the final answer? Let me get to number 3.
Yep.
Or no, yeah. Okay, so I wrote the equation down correctly. We're looking upward.
I only took 1 point off. Yeah. Or you didn't put the,
Yeah, I wrote the equation down right, and then for some reason worked it out incorrectly. I don't know what happened.
got me on that one, brother. Jay, I think.
I was asking about the same question. I was just seeing what the answer was.
Oh, yeah.
Okay. I'm not sure what I was
Do you mind explaining this a bit? 'Cause my understanding was it had to be above the cutoff frequency.
It is.
Okay.
The cutoff is what?
I meant below.
No, above.
Oh, okay.
It's a waveguide, only high frequency pass in a waveguide. So if you take the long dimension A, well, A is lambda over 2, right? So 2A is lambda, lambda C over F cutoff, and you can calculate F cutoff is 2A over C.
And I did that, yeah. 2 hours here?
That's it, that's it. All right, now if that's the cutoff, if 4 gigahertz is greater than that, it propagates.
Okay. I got it the wrong way around.
No. It has to be higher than that to propagate. Remember, a waveguide, the way you think it is, the wave has to fit in the guide such that it at least has a null to null. So if this, you think of a sine wave, all right? A sine or half wavelength has to fit in that guide over the long dimension. If it doesn't, it doesn't fit in the guide and it becomes an evanescent mode and it just shorts right out.
Okay. So roughly that.
Okay, first, test
Plus-
already been through.
No, you gotta add, here's what you do. You take your score, multiply by 2, you get a number. Then you add 10 points to it.
Yeah.
Oh, okay.
Just out of curiosity, do you know what the class average was?
You would ask that. Yeah, I think it's 81 or 82.
Oh, dang it. Never mind.
But I'm not sure. I mean, the high score I think was 94 or 90,
Okay.
somewhere in there.
Actually, you had a question about linear sequence.
Sure.
You don't care about answering that?
No, I'll be happy to.
So I'm currently trying to do a independent research with Dr. Roth, looking at different topics I've been proposed to.
Okay.
And one of the topics I was thinking about was active noise cancellation for drones or other robotics. And my question was, I was
Noise cancellation.